Working? Yeah. All right, welcome to the colloquium. It's a great pleasure to welcome back Professor Chandrashekhar Khare from UCLA, who will tell us about modularity of Galois representations from Ramanujan to Serre's conjecture.
Okay, so that. All right, so yeah, thanks so much for the invitation. I'm spending my sabbatical year, most of my year here, so I've just started, and it's good to be back. So I'm going to talk about something which actually I've not worked on recently. It's some work which I did maybe, I don't know, 10, 15 years ago, but in the last few months, I've been going around giving talks on similar topics. A friend of mine, Basi Dixhoven, passed away, unfortunately, very early, earlier this year, and I gave a talk in his memory maybe a few months ago. And he had written a book on efficient algorithms, or at least theoretically good algorithms to compute the Ramanujan tau function, tau of p. So I kind of looked at that book and then kind of gave a talk related to that. So somehow I've kind of been talking about this for the last few months. If you want to hear more about what I'm doing currently, I'm going to give a talk at IIT Bombay in a couple of weeks, in which I'm going to talk about other kinds of modularity, which will be closer to the work I'm doing right now. All right. Anyway, so this is something about Serre's conjecture and the relation to the Ramanujan tau function. So I'm going to kind of draw a line between this old paper of Ramanujan in 1916 called on some arithmetical functions. It was published in 1916, and it's had a remarkable influence on the development of number theory across the 20th century. So I think in some sense one can make an argument for the fact that that paper set off a set of developments which led eventually to Weiss's solution of Fermat's last theorem via the work of Serre and Swinnerton-Dyer in the 1960s and 1970s to try and understand some of Ramanujan's remarkable observations, particularly to do with the prime 691. Okay, so I'll come to the prime 691. So this is going to be some sort of historical kind of lecture. Just I'll be telling you a story, but in the end, maybe I'll kind of tell you something which is a little more modern in terms of, as I said, Basi Dixhoven's book, along with several others, where he came up with an algorithm which uses kind of Galois representations to compute some coefficients, which are the Ramanujan tau function. And also I'll end with some question which I've kind of thought about for many years, which I've made no progress on, about counting certain sorts of two-dimensional mod p representations of the absolute Galois group of Q. So somehow that's the plan. Most of the talk is going to be somewhat historical. And kind of maybe I started thinking about Serre's conjecture when I came back to TIFR in 1995 after my PhD. So okay, so maybe this is going to be catching up with some of that. All right, so Serre's conjecture, and Serre himself in the paper he wrote in Duke in 1987 or published in 1987, he kind of thinks of his conjecture as a part of a mod p Langlands program. At that time, perhaps it was still somewhat fledgling, but since his work, I mean, various aspects of his conjecture have kind of fitted into or have given rise to developments which are now thought of as being part of the p-adic Langlands program or the mod p Langlands program. So, and also Serre's conjectures are just the first kind of conjecture one can make. There have been vast generalizations of the conjecture, but the proof has not, I mean, the only case which has been proven is Serre's original conjecture. So in some sense, though I'm talking about some result which is 10, 15 years old, in some sense, in terms of the global theory, there has been no further results, right? So this is Serre's original conjecture is that which is proven, but conjecturally the thing has been generalized to many more situations. And some more technical aspects of the conjecture, like his definition of weights and so on, has played a big role in the this kind of mod p or p-adic Langlands program. So also in the mod p Langlands, one might wonder, is it some kind of niche kind of technical thing? But on the other hand, it does kind of imply the characteristic zero kind of cases which people have traditionally cared about. For example, Kolmez, I mean, Serre credits Pierre Kolmez with the observation that his conjecture implies the modularity of elliptic curves over Q. Right, so this is a case of the Langlands program which predated Langlands. In Taniyama, in some vague form at least, had thought about this question of how you can relate elliptic curves to modular forms.
And when is the work of Kolmez?
Sorry?
When is the work of Kolmez?
Kolmez, yeah. I mean, so Serre, of course, this deduction is made in Serre's paper, but he credits Kolmez with with pointing out the observation. Yeah. All right, and so in fact, many years ago, so soon after I started working here, I observed that Serre's, I mean, it's a very small observation again, but I observed that Serre's conjecture implies Artin's conjecture for a particular case, two-dimensional odd representation. So the mod P version of the Langlands program, which of course does imply the characteristic zero version, because for example, Artin's conjecture is considered kind of one of the sort of important cases of the Langlands program. So it's about some holomorphy of L series attached by Artin to two-dimensional or n-dimensional representations of Galois groups. All right, so okay, so I want to talk about some of these things, but I'm going to go back much further. I'm going to start with Ramanujan's 1916 paper, where he makes some observations about the tau function. So I'm going to define what the tau function is, and in fact, these observations kind of influence the subject right throughout. And in fact, when Jean-Pierre Wintenberger and I started proving the Serre's conjecture, somehow the first cases we proved of Serre's conjecture were related to the Ramanujan delta function. So the Ramanujan delta function did play a key role even in the formulation of Serre's conjecture, what led to the formulation of Serre's conjecture, and in the initial results to do with Serre's conjecture. Any questions? All right, so let me start. I mean, so kind of preparing for this lecture, I kind of looked at Ramanujan's paper. Yeah.
Okay, what is the relation between tau and delta function?
I didn't. All right, I didn't kind of quite follow the question. Yeah. Okay, maybe I'll kind of move on. So okay, so in this paper, he just starts with this infinite product. It's like some sort of generating function, and then you expand it in powers of x, right? And the coefficients of the expansion are called the tau function, right? So you start with this function. And this is the function he studies initially purely as a combinatorially kind of defined series, and he kind of made a study of these coefficients tau n. Okay, so now the other functions which kind of play a role in this are these more elementary functions. So the sigma k function, which is just the sums of divisors of when sigma k of n is just the sum of divisors of n raised to the kth power, and then you kind of regularize it and define it for sigma k0 to be a half of the zeta function evaluated minus k. Now this might seem unmotivated, but somehow it's related to expansions of Eisenstein series. Okay, so this is just a definition of an elementary arithmetic function, okay, which is the sums of divisors function. And in fact, Ramanujan's paper is concerned to begin with these functions, or some sort of things you do with these functions. All right, so this is the function which he's going to convolve. Okay, so Ramanujan starts his paper by looking at this kind of sum he defines, which is summation Rs of n, right? So which is some convolved sum of these sigma R sigma S. So it's this particular thing, right? So it's so you fix a positive integer as R and S, and you kind of define this function sigma Rs of n to be this summation, right? Sigma R0, sigma Sn, etc. And then somehow he wanted to find formulas, find kind of ways of estimating this, or kind of studying this convolved sum of the sigma function. And he found, and he wrote it in the following way: some of the dominant terms when you try to kind of evaluate this thing are these functions, or these first two terms, right? So somehow they are again to do with the sigma function, sums of divisors function, but except you look at sigma r plus s plus 1 of n while you're convolving sigma r and sigma s. And there's also this, so somehow these two terms, right? The two leading terms coming from the sigmas or indexed by different integers, r plus s plus 1 and r plus s minus 1. Now, typically, I think one is going to be interested in r and s odd, and somehow this convolved sum in the theory of modular forms is going to come from multiplying Eisenstein series. And okay, so anyway, so somehow this has something to do with multiplying Eisenstein series in the case when r and s are both odd. And then r plus s plus 1 and r plus s minus 1 also both odd. Okay, so somehow you kind of look at this convolved sum, you write it in the following way, and then there's an extra term which you don't quite know about, and that is the error term, right? So somehow you write it in terms of the first two main terms, and then Ramanujan calls it ERSN, and the gamma is the usual gamma function, and zeta is the Riemann zeta function, right? So and ERS is some error term. Okay, and somehow in that paper he wants to evaluate this. He wants to say something about these convolved sums. Okay, any questions about? All right. Okay, so now, for example, for certain values of R, what matters somehow mainly is R plus S. So when R plus S, for example, is 6, then this error term is 0, and then you get some explicit evaluation of this convolved sum of sigma 33n. Right, so that's kind of, it's related to sigma 7n, and it's the coefficients come from the gamma and zeta functions. Okay, but now Ramanujan's particular interests are somehow if R plus S equal to 10, something interesting happens. Then this quantity ERSN is not equal to 0. And then Ramanujan observes that the kind of error term is then connected with this function tau n, which I've defined, right? Which was defined kind of as something just combinatorially in terms of some power series and so on. Right, so some of the analysis of ERSN is and this ERSN turns out up to scaling, it turns out to be the same as tau n. Right, so that's for R plus S equal to 10. For example, a good number to keep in mind for R plus S equal to 10 is R equal to 3 and S equal to 7. Right, so some of that has to do with certain modular forms of weight 4 and 8, Eisenstein series of weight 4 and 8. Okay, so somehow I mean, okay, so that's what he was actually interested in, and he wanted to estimate these error terms, ERSN, and somehow find properties of these error terms. Okay. So okay, but now to understand kind of this in a more kind of maybe standard language, now we are going to switch to the world of modular forms, and we are going to instead of thinking of this power series in terms of x, and we're just going to set x equal to e raised power of 2 pi I z, right? And now rather than thinking of it formally, I'm going to think of it the corresponding thing you get as a modular form, right? It turns out to be a certain Cuspa form of weight 12. All right. So okay, so what is the space of modular forms? It is certain functions on the upper half plane. We define them mk SL2ZC. So these are modular forms of weight k on the full modular group SL2Z acting by Mobius transformations on the Poincare upper half plane. And these are functions which have a Fourier series. So they're invariant under ZZ plus 1, and they have this kind of following Fourier series. Summation a n qn for n bigger than or equal to 0. And then they have this more subtle symmetry under Mobius inversion, which is that f of minus 1 upon z is equal to z to the k times f of z, right? And the k is a weight. So the weight enters in terms of the transformation property under Mobius inversion. Okay, so these are only modular forms of level 1. And their interest as far as the Ramanujan tau function is that the tau functions are going to be Fourier coefficients of a particular modular form of weight 12 in level 1. Okay, so because this group SL2Z is generated by these transformations, z goes to z plus 1 and this Mobius inversion, you have a richer kind of, apparently richer symmetry, f of a z plus b upon cz plus d is equal to this thing, cz plus d to the k times f of z. And so we got within the subspace of modular forms of weight k, you can also consider a subspace whose a constant term which vanishes at infinity. So that is called the space of Cuspa. And typically it's of codimension 1 in mk. And somehow this mk is 0 unless k is bigger than or equal to 0 and is an even integer. And whenever k is bigger than or equal to 4 and even, then mk, the space of weight k modular forms on SL2Z is non-zero. Right, so somehow these are some basic facts about these modular forms, and the fact that mk vanishes for k odd for the group SL2Z has some consequences in terms of the Galois theory. It can kind of Galois representations which spaces of modular forms can account for. Right, somehow there's a parity constraint on the side of Galois representations of that. Okay, so. Okay, so now some particular modular forms one can write down just by sort of some averaging process are these explicit forms of these Eisenstein series of weight k, and they have this particular Fourier expansion, and they certainly make sense and are non-zero for k bigger than or equal to 4 and even, where the non-constant Fourier coefficients are these simple arithmetic functions which Ramanujan was interested in, sigma k minus 1 n, right? So sums of divisors of n to the k minus 1. There's a somewhat more mysterious constant term which has to do with the zeta function. And it's the Cade-Bernoulli number, and yeah, but it's the non-constant Fourier coefficients at least are rather explicit and simple, right? So there's always one modular form in this space as long as k is bigger than or equal to 0, k is bigger than or equal to 4 and even. And somehow one normalizes this so that the constant term is 1. You kind of make it 1 by multiplying it, by scaling it. And the way Eisenstein series of weight 4 and 6, which Ramanujan in this paper in 1916 denotes by Q and R, and they've been called that since then. They play a somewhat significant role. Yeah, so this E4 and E6 have some sort of special role in the theory. And in general, I mean, so one has a decomposition that the space of modular forms of weight k is the direct sum of the line spanned by the Eisenstein series plus the complementary space, which is the space of Cuspa. Right? And some of the error terms Ramanujan was studying, r plus s equal to less 6 and so on, the fact that the error terms are 0 were partly because of the fact that the space of Cusp forms vanishes for more values of k than the space mk. Right? The first time you have a Cusp form is of is for k equal to 12. I cannot hear any of the questions. So should I ignore them or yeah, I don't know. Yeah, maybe later on I can. All right, and you can put together modular forms or put them all together by looking at the direct sum over the space of modular forms of weight k. And this turns out to be a polynomial algebra in these two modular forms of weight 4 and weight 6, which are called Q and R. And it's somehow some sort of it's a graded algebra, and provided you give the weights 4 and 6 to these two Eisenstein series. And okay, so the other things, other kind of gross thing, other kind of general things one can say about the space mk is that you can have a formula for the dimension, which is the dimension is roughly k by 12. And the space of Cusp forms vanishes for all k less than 12. And the first time it does not vanish, it's one dimensional for S12, SL2Z. And it is the corresponding space, I mean, delta, the delta function, which you get by evaluating this earlier series F, which I'm going to rewrite, at Q, right? It's a Cusp form, and it's the first Cusp form of, it's the Cusp form of smallest weight in level 1. Yeah. So it's kind of the first time something appears, it's perhaps interesting to study. So some of this thing has been much studied. Of course, the delta function, you can view it as a function on the moduli space of elliptic curves, that it is related to the discriminant of elliptic curves, and it's been studied since the 19th century. But Ramanujan kind of made some remarkable observations about the Fourier coefficients of this delta function, right? And so it's called the Ramanujan delta function because of his deep study of it. Okay. So this Ramanujan delta function in terms of this Q and R is kind of a homogeneous polynomial of degree 12. If you remember that Q and R have weights 4 and 6, and it's written this way. And it has the Q expansion, which we started with, and it has a Fourier expansion, which by definition is summation tau and Qn. Right, so somehow this is the Ramanujan, and then Ramanujan in the paper makes three conjectures, or makes a few conjectures about these functions. He conjectures that the function is multiplicative in the sense tau mn is equal to tau n and tau times tau n when m and n are co-prime integers. Then there's kind of a more complicated formula for tau p to the n plus 1. It's tau p and times tau p times some correction term, or minus p to the 11 times tau p to the n minus 1. And then there's this kind of remarkable observation that tau p is conjecture. He conjectured is less than or equal to 2 times p to the 11 by 2. 5.5. The exponent is 5.5. And somehow Ramanujan was interested in these kind of estimates to get a bound on the error terms in his representation of this convolved sum sigma rsn in terms of some two main terms and then error term, right? He wanted to bound the error term. So he had some bounds on the error term, but he wanted something as sharp as possible. And this kind of was what he thought was the. Okay, so for example, in Ramanujan's paper, you can find a table for the first, for tau of n for the first 30 values of n. Right, so somehow he can, it grows fairly rapidly. And on the basis of this, or perhaps he had probably computed more in his head on scratch paper, he made these conjectures, right? So, okay, so these conjectures have turned out to be pretty influential. Okay, so for example, he has some estimates on these sort of ERS and N, or equivalently the tau function for r plus s equal to 10. And he gets some estimate that's roughly of order at most n to the 7. In fact, you can probably say n to the 6. But he also kind of sort of wanted the best possible estimate, and he thought this was the best possible estimate, right? That the exponent should be 11 by 5.5. And right, so this is this Ramanujan conjecture, which has become a sort of paradigm of it's a general conjecture for automorphic forms, was made first in this context. Okay. All right, so the first two properties, which were the multiplicative properties of the tau function, were proved pretty rapidly within a year or something after Ramanujan conjectured them. And the way and then they were proved by Model, and he introduced operators, which later on got called Hecker operators. Hecker studied them further and deeply. he introduced certain operators on the space of modular forms that commute with each other and can be diagonalized. Now these operators are kind of have some meaning because these spaces of modular forms can be thought of as functions on lattices and etc. So you can look at some averaging function. So these operators, these Hecke operators, T sub n has some meaning, and using this meaning, one can somehow prove for these operators the properties Ramanujan had conjectured for his tau function. Right, so these operators T sub n, indexed by natural numbers n, have the same properties which Ramanujan had conjectured for tau n. Right, so tau mn, Tmn is equal to Tm times Tn for mn co-prime, and this kind of more complicated thing for powers of T. Yeah, so he kind of, and then this was amenable to prove because somehow these Hecke operators had some kind of group theoretic meaning. Okay. And so the other property of this thing, so this is a space of operators, that is an algebra of operators acting upon this finite dimensional complex vector space, preserving the space of Cuspa forms. And furthermore, if you look at an eigenform for these Hecke operators, then first of all, the first Fourier coefficient is forced to be non-zero, otherwise the thing will be 0. And then you can normalize it to be 1. And then there is a link between the eigenvalues of this of f acting upon Tn and the Fourier coefficients. Right, f acting upon Tn acting upon f, the eigenvalue turns out to be exactly the nth Fourier coefficient of f. Okay, and then these explicit modular forms of weight k and level 1 I wrote down are indeed Hecke eigenforms for Tn with eigenvalues, the Fourier coefficient sigma k. Right, and it turns out then that that the delta function, which is now the up to scaling the unique Cuspa form of weight 12, is an eigenform for these Hecke operators. And as I said, and it is a normalized form, and the first Fourier coefficient is 1, and it's an eigenform. So delta z TL is equal to tau L delta z, and TL, so Tn satisfy the properties Ramanujan conjectured for tau sub n, tau of n, and so model deduced the first two conjectures of Ramanujan because the corresponding operators had that property. Right, so if the operators have that property, then the eigenvalues will be forced to have the property. So that's how model proved these first two conjectures of Ramanujan within a year or so of pretty. So I guess this is some kind of we use some anachronistic term. I mean, this is some kind of idea of categorification where it's, rather than proving just properties of numbers, if you don't have any structure, it's hard to prove anything about them. You kind of realize them as eigenvalues of operators, prove something for the operators, and hence deduce the same for the eigenvalues. Right. So somehow we'll see this sort of trying to conceptualize at a higher level some of these things to prove more properties of them. Right. So that's kind of how the subject has gone. Okay. So now, for example, in fact, in Ramanujan's paper, I don't know whether he writes down those properties in the way I've stated. He actually just considers this kind of the Dirichlet L series, or whatever, this L delta S, which is the summation tau n to the S, and he conjectures that this L delta S has an Euler product expansion of degree 2. In the sense, L delta S is a product of certain factors which are more elementary and which have to do with tau p. Right? So it's product over primes p of this particular Euler factor, which in some sense is thought of as an Euler factor of degree 2. You can think of this as the polynomial 1 minus tau p x plus p to the 11 x squared evaluated at x equal to p to the minus s. Okay, so somehow this is an Euler factor of degree 2. And okay, I'm going to skip what Hecke did here. So in some sense, this was the first appearance in mathematics of a L function with Euler factors of degree bigger than 1. Right? Dirichlet in the 19th century had considered in his famous proof of the primes in arithmetic progression, he had considered Dirichlet L series, which were L chi S, and they had Euler product expansions of degree 1. Right? So this Ramanujan delta function, which again kind of showed up for Ramanujan in this kind of somewhat exotic way, as error terms of these convolved sums, turns out to be a L series, gives rise to an L series with a Euler product expansion of degree 2. Right? And this Euler product expansion is equivalent, at least formally, to these two properties I wrote down for Ramanujan's. Yeah, any questions? I don't know. Okay, so now the third property actually turned out to take some proving, and it was not proven for maybe 6 decades after he first conjectured it. So almost, I mean, if you just try to get the bound to be p to the 6 rather than p to the 5.5, then it's rather easy to prove. You can prove it as a consequence of the maximum modulus principle. And so, for example, I mean, this conjecture, one would wonder what is the importance of it. Hardy was skeptical about the importance of this sharpening, and he said we seem to have drifted into one of the backwaters of mathematics. But he qualified this by saying that the problem might have some interest because Ramanujan had identified it as an interesting thing. And on the other hand, the conjecture and its natural generalizations have turned into one of the central problems in the theory of automorphic forms. Right? So Ramanujan was pretty prophetic in terms of latching on, thinking about this property or concentrating on this property. Right? And the kind of context in which it arose, maybe I don't know. At least certainly, I've never thought about these convolsums. I don't know how much people study these convolsums these days, right? But it arose in this context. But on the other hand, the importance of the conjectures is has been much larger than the original context in which Ramanujan looked at this. All right, and the other thing which so this was some stuff about multiplicative properties and Archimedean size of tau n. Ramanujan also discovered a remarkable congruence for tau n, which has been again very influential in various developments in number theory, which is that tau n, though tau n itself as a function has no simple formula, right? It's some kind of mysterious function, but sometimes modulo primes, he discovered that mod 691, which is a fairly large prime, it is very simple, right? It's congruent to this kind of simple arithmetical function sigma 11n, which is just the sum of divisors of n to the 11th power. And somehow the 691 has something to do with the fact that 691 divides the numerator of the 12th Bernoulli number, which happens to be the constant term of the Eisenstein series of weight 12. Right? So there's some reason why 691 appears here. Okay. Okay, so this was now this congruence also I think in some sense directly played a role in the developments which led to Serre formulating his conjecture. So okay, after Ramanujan, several people, English and Indian mathematicians wrote down similar congruences for primes 2, 3, 5, 7, 23, 691. So 6 of these primes. Sometimes the high powers of these primes, not just, so for example, 2, their congruence is mod 2 to the 11, etc. Right? And the feature of these congruences is that these are always something like tau n is congruent to something related to the sums of divisors functions, but not exactly. Sometimes there's some. Okay, so now the question is, I think maybe Swinnerton-Dyer and Serre decided to try to understand why are there these congruences and why are there no other congruences people have discovered modulo other primes. Right, so there were these 6 primes which are called exceptional primes for the Ramanujan delta function, for which there were sort of congruences for tau n. So tau of L was equal to L to the A plus L to the B or something for some fixed A and B, mod those primes. But no, so only for these primes. Right, so then so the explanation for these congruences given in the 1960s and the Ramanujan bound, right? So the proof of all these arose. The answer lay in the Galois representations associated to the delta function. Okay, so Serre in this seminar, Piso Porto in 1967-68, conjectured that there should exist a L-adic Galois representation, right, in GL2 of the L-adic numbers, which are some sort of putting together of Z mod L to the R for various R's, right? So he conjectured that the L-adic representation associated to the delta function of the absolute Galois group of Q, so the Galois group of Q bar over Q, and the tie with the link with the delta function is that this representation is unramified outside L, which is to say somehow that the fixed field of the kernel of this representation is made up of number fields with discriminants which have only powers of L in them. And once some representation is unramified at a prime P, somehow locally at that prime P, this representation becomes rather simple. You just need to know what happens to the Frobenius at P. There's some kind of marked conjugacy class. And so then the tau function appears in the characteristic polynomial of this L-adic representation evaluated at this Frobenius at P. Right? So if you look at the characteristic polynomial of rho delta L at Frob P, then it has this particular form, x squared minus. So the trace of this Galois representation at P at Frobenius at P is tau P, and its determinant is P to the 11. Right? And 11 is somehow 12 minus 1, which is the weight of the delta function. Okay, so in fact, again, so Serre conjectured this in 1967 or something, and then within a year or so, Delin actually proved these representations existed. Of course, Serre was not plucking this out of thin air, because such representations were known to be associated to new forms of weight 2. Okay, maybe there's a typo here, k equal to 2, it should say. And Levelin had been constructed by Eichler Shimura in the 1950s. But for that, they had the crutch of abelian varieties available. So somehow it's a simpler construction, where it was known since the 1950s that you have such Galois representations associated to Hecke eigenforms. Right? So the novelty of Serre's conjecture, or the thing he was considering, was that the weight was higher than 2, it was 12. And there was also work of Kuga Shimura, which was kind of certainly related to this. Okay. Okay, so now up the categorification ladder, now that numbers tau p have acquired a more sophisticated meaning as traces of Frobenius in some Galois representation. Right? And then somehow Deligne proved this conjecture and realized these representations geometrically. And then later on, after 6-7 years, in 1974, he proved the Weil conjectures, right? So which gave bounds on traces of Frobenia acting upon some kind of cohomology groups. And as a result, he deduced this bound, right? So it was a very, very elaborate proof. And it took 60 years, right? And it required development of Étale cohomology and construction of the map from modular forms to Galois representations and realizing these Galois representations in some geometric way to prove this conjecture, right? It took some proving. Okay. Recently, in fact, there's been some development where you get a proof which is not geometric in nature in this sort of 10-author paper, but okay, but still, I mean, it still takes some proving. Yeah. Okay. So now the other thing what I want to focus on in the remaining half an hour is this congruence mod 691 and how it led to Serre's conjecture. So, right, so the congruence mod 691 is equivalent to the fact that if you look at this 691 adic representation associated to right. So if I look at L equal to 691 in this L-adic representation. Okay. Yeah, look at it. So you look at this into GL to Z mod Z691, and you can reduce it mod 691. Right? Then you get a mod 691 representation. And the congruence of Ramanujan, which is this tau n congruent to sigma 11 and mod 691, can be re-expressed Galois theoretically as saying that if you look at this Galois representation mod 691, it degenerates in the sense it has smaller image than perhaps all of GL2. And so it's an upper triangular representation. And on the diagonal, you have the trivial character and the mod 691 cyclotomic character, which observes the action of Galois on 691st roots of unity to the 11th power. Right, so it has this particular shape, so there somehow it becomes reducible. The Galois representation, which generically is irreducible, as it turns out in this case to be reducible, which accounts for some of these this congruence. Okay, and this again played a big role in the work of Ribbit in the 1970s on things to do with class numbers of cyclotomic fields. Okay, so now Serre and Swinnerton-Dyer proved that, in fact, even before I think Deligne proved these representations existed, they axiomatically just assumed these representations existed with the given properties, which told you what the traces of these representations were at Frobenia elements. And they kind of started a deep analysis of what the image of such a Galois representation is. So they proved that that this L-adic representation has big image, so it contains SL2ZL, the SL2ZL for L different from these exceptional primes, and in general has pretty large image, right? It has open image in GL2ZL for all L, or at least, yeah.
Where do the exceptional primes come?
Yeah, so these are some of these exceptional primes. 2, 3, 5, 7 are there just because they're small and they're less than the weight. 23 is some kind of an eccentric prime, but it has, yeah, I don't know. It has something to do with, again, maybe it can be explained with respect to something called Ramanujan's theta operator. And 691 is because it divides the 12th Bernoulli number. But yeah, these small primes always kind of occur, maybe, but 23 and 691 are somewhat sporadic primes. Yeah. Okay, so I'm going to scan and okay. Well, that's so. If there's any students in the audience, kind of they as part of their analysis, they proved a simple group theory lemma that if you have a closed subgroup of GL2ZL, that mod L contains SL2FL, then the L-adic thing contains SL2ZL, right? Some sort of Nakayama's lemma in this situation. All right. So, in the context in which they were, I mean, Swinnerton-Dyer, I think, observed the following congruence also, which plays a role in the story. So you can look at this delta function, right? It has this Q expansion, and then now you read it mod 11 just formally, right? Without worrying, maybe you just read it formally in terms of. So now you can use Fermat's little theorem or whatever the high school version of the binomial theorem to factor 22 as 2 to the 11 and take 11 inside. Right, so you get this particular Q product expansion, and that turns out to be related to a Cusp form of weight 2 and level 11. Right, so the delta function mod 11, so the delta is a weight 12, but mod 11 it looks like a Cusp form of weight 2 on a slightly smaller subgroup. Right, and this is the L equal to case of a general sort of thing Serre proved. that you can sometimes reduce the weight at the expense of increasing the level. Right? So all these kind of themes play a big role in Serre's conjectures and so on. I mean, because somehow the concept of a modular form becomes malleable mod L, kind of there are many congruences, and the congruences play a big role in the theory. Okay, so for example, what did Serre and Swinnerton-Dyer exactly prove? So they proved that this L-adic representation is an irreducible representation, and it's odd in the sense when you evaluate it at the conjugacy class of complex conjugation, then it gets mapped to 1, 0, 0, minus 1, and not a scalar. They also proved for L outside this exceptional set, or in fact, okay, the reduction is absolutely irreducible, which is a stronger statement than the L-adic thing being irreducible. For L equal to 23, it has some exceptional behavior, which I'm going to skip. And the determinant of rho delta L is the 11th power of the L-adic cyclotomic character, which kind of gives you the action of GQ, or the absolute Galois group of Q, on the L power roots of unity. And for L not equal to these exceptional primes, the image is not only irreducible, but is large, right? It's non-solvable. It contains SL2FL. Okay, so this kind of this they did as a result of some rather beautiful and deep study of congruences between modular forms, right? So this is work of Serre and Swinnerton-Dyer, which was first reported on, I think, by Serre in a seminar Bourbaki talk, maybe in 1972 or 73. And then I think also Swinnerton-Dyer wrote some article in one of the Antwerp proceedings. Okay. All right, and somehow once you show that some of these mod L images are large, in particular non-solvable for outside this exceptional set, then one can then somehow say that there cannot be some simple-minded congruences for tau and mod L, right? So I'm going to skip this again. Again, you can just once you know this what the images of these Galois representations are, you can rule out there being simple congruences for the tau function modulo any prime L outside this exceptional set, right? So the congruence on P does not determine any congruence on tau P outside this exceptional set of primes. All right. So this is what Serre and Swinnerton had done. Now let me. So this was the forward direction where you go from a modular form to a Galois representation. Serre's conjecture is the statement in the opposite direction. So it's kind of a reciprocity statement, though Serre doesn't like it to be called reciprocity. But anyway, so if we denote by K delta L the extension of Q through which rho bar delta L factors, right? Then this extension has the following properties. So now we are looking at the delta function. We are looking at it, looking at its model representation coming via some fancy construction of Dedin. Of course, mod L somehow the construction is easier because somehow you can also realize these representations as coming from abelian varieties. And this the extension cut out by rho bar delta L has the following properties. It's a finite. It's a number field. It's unramified outside L in infinity. The Galois group of this extension embeds inside GL to FL. If L is outside this exceptional set, then the image of this then the Galois group contains SL to FL. Under this embedding of the Galois group into GL to FL, the determinant of the matrix is -1 of complex conjugation. And okay, so somehow this is telling you something about this representation in terms of the Galois group and its local ramification properties, right? It's unramified outside L in infinity. But somehow now to tie it to the delta function, you need more information. And somehow you need to know what's happening for this extension at L. What are the ramification properties of this extension at L? So somehow, I mean, the ramification property is that under this embedding of the Galois group into GL to FL, the inertia group at L gets mapped into one of two possibilities, right? It's either up to semi-simplification. So it's either the identity plus the 11th power of the mod L cyclotomic character, or it has some different behavior, which I'm not going to go into because that happens very rarely, as we'll see. Okay, so then it becomes in the second situation, the local representation at L is irreducible, and on inertia it has this shape. Okay, so in fact this dichotomy, these two cases are related to the property of tau L mod L. The first case occurs whenever tau L is prime to L, and the second case occurs when the local representation is irreducible, when L divides tau L, right? And somehow when this, I think, for example, when Serre wrote this seminar in 1967, perhaps the only values he knew when tau L is congruent to 0 mod L are perhaps 2, 3, 5, 7, or maybe he also knew 2 for 1, 1, I don't know. But later on in the few years ago, I don't know exactly, but someone found this frighteningly large value for which tau L is congruent to 0 mod L, right? It's 7 billion and something. So, but still, though this phenomenon of tau L being super singular at L, which is this tau L congruent to 0 mod L, is widely expected to be very rare. But still, one does not know that the contrary case, which is called ordinarity, one does not know tau L is ordinary at L for infinitely many L, right? So it's kind of some mysterious thing where, though you expect it to happen overwhelmingly often, you don't even know it happens infinitely often. Okay, so somehow it's okay. So these are the properties of this field extension. So now we are converting a modular form into a field extension, right, indexed by the primes L, and the field extension somehow has something to do with Galois groups like GL2FL, and they're unramified outside L in infinity, and they have some more detailed behavior at L. There's some ramification behavior which is captured by the weight of the modular form, related to the weight of the modular. Okay, any questions? All right, so now the rough version of Serre's modularity conjecture, at least for the delta function, things supposed to be arising from the delta function, would ask that any such extension, suppose you look at an abstract extension of Q with Galois group, something roughly like GL2FL, and it is unramified outside L in infinity. It's odd at infinity in the sense the image of complex conjugation is not scalar in the Galois group. And somehow the inertial behavior looks like it comes from weight 12, which is to say it has one of these two behaviors, right? So somehow it's a more constrained kind. Then one would ask, then one could ask, is such a extension equal to K delta L? Right? So somehow it's a converse question. How can you characterize which extensions with certain properties come from the delta function? Right? So this was in some sense the first case we proved in roughly 2004 in work with Jean-Pierre Wintenberger, and yeah, it was one of the. So if we had okay, so I'll come back to this. So if we drop 5, right, if we don't really try to specify what the ramification at L is doing, then the rough formula conjecture would say that any such extension comes from some new form of level 1 without knowing the weight, right? And if we further drop the condition of being unramified outside L, then the conjecture predicts that any GL2 FL type of extension, or FL bar extension, which is odd and with certain properties, comes from some modular form. Right, so somehow this delta thing is just a very special case of the conjecture, but okay, so it's one of the first cases we proved. So example for L equal to 11 is the conjecture predicts if you have an irreducible odd representation, unramified outside 11 and satisfying the condition on inertia at 11, right, which would be, in this case it would be something like inertia goes to the mod 11 cyclotomic character star 01, for example. Then Serre's conjecture and this congruence I recalled above of Serre of Swinnerton-Dyer between delta and S2 gamma naught 11 would predict that rho arises from the Levin torsion of one of the two elliptic curves over Q of smallest conductor, namely 11, right? So somehow this is again an embodying of some abstract representation. It's just some abstract Galois theoretic object, as long as it has some properties which are purely local in nature. Then one kind of tries to embody it, tries to realize it from a much more concrete source, like a modular form or an elliptic curve. Right, so somehow that's the nature of the conjecture. All right, so more formally stated, Serre's conjecture is about two-dimensional representations of the absolute Galois group of Q into 2x2 matrices invertible over a finite field.
But he knows who has written it.
Sorry?
Mahoney.
So, and it says that if you have a representation which is odd, in the sense that the image of complex conjugation is not a scalar, or rather, at least, to be more precise, one should say the determinant of image of complex conjugation should be -1, because for L equal to 2, there's some extra. Then it should arise from a new form, right? So this is the conjecture. So it characterizes two-dimensional representations which come from new forms, right? Representations which come from new forms certainly have this oddness property. They're typically irreducible. So Serre's conjecture is the converse to this thing. Okay, so this was the conjecture, right? Any questions? So of course, if you're seeing it for the first time, this is one has to stare at it a little bit. So it's a two-dimensional representation of the absolute Galois group of Q. It's always going to have some finite image, though the field might be FL bar. That's the notion of continuity. And it's going to factor through some finite Galois extension of Q. And it's irreducible. Okay, absolutely irreducible. And it's odd, which is to say it's in the determinant of complex conjugation is -1. So then this oddness is related to the fact that the modular forms in level 1, for example, vanish for weights which are odd. Okay, and yeah, such a representation comes from a new form. Okay, so this was the conjecture. And he in fact made a more precise conjecture. So as I say, he first made this conjecture in a letter to Tate in 1973, and then published a small note about it in 1975. But then stimulated by kind of Frey's brilliant idea about kind of deducing Fermat's last theorem from these type of conjectures, he kind of made these invariants from which the Galois representation arises more precise, right? So he defined the level n rho, which somehow was some off-the-shelf definition using the notion of a conductor which existed before he did this. On the other hand, he made a very artisanal definition of the weight, which has been very influential in the Mod P Langlands program. Right? So somehow this the Duke paper, one of the main innovations or one of the main developments is to define the weight precisely. Right? It takes 7-8 pages. It's purely by hand, right? But somehow it's a rather intricate definition, so that it's consistent with various things he and Tate and various people had proved about modular forms. Okay. Okay, so and somehow this refinement of the Serre made of his conjecture from 1975 to 1987 was, as I said, stimulated by Frey's observation relating Fermat's last theorem to modularity of Galois representations. Okay, so now remarkably, Tate by return post, right, when Serre wrote to Tate in 1973, within a month or so, or he replied by proving his conjecture for L equal to 2. And that the argument he used was extremely elementary but beautiful, kind of using only basic algebraic number theory. Somehow the argument was that you get upper and lower bounds and fields cut out by these representations, right? And somehow the upper bounds come from arguments to do with ramification, and lower bounds come from Minkowski's estimates on discriminants of number fields. And then somehow he showed that for mod 2, if you have a representation of GQ into GL to F2 bar, which is unramified outside 2, right, and which is then it is forced to factor through Q zeta 8. Right, or something. He made some very explicit kind of thing, and the entire argument relies on the numerical fact that 2 to the 5.5 by 2 is less than pi e squared upon 4. Right, so somehow it relied on, and it's quite pretty close. It's 5.65 is less than 5.8. So Serre observed that if you can use Tate's argument for L equal to 3 using slightly better and bounds on Odlyzko or on discriminants due to Odlyzko. For L equal to 5, Schad and Brueggemann later kind of proved similar statements, but after a while this argument just doesn't work, right? For L equal to 7, for example, there's no way this kind of argument can work. And nonetheless, these initial cases proved by Tate were a starting point for our proof of Serre's conjecture. Well, our proof of Serre's conjecture uses an induction on the prime L, and the initial cases are supplied by Tate's very nice and very elementary proof, which has nothing to do with modular forms, right? It's a purely algebraic number theory. So one needs accidents. One needs to be lucky somewhere to be able to, yeah, so this is the piece of luck. Okay, so Fermat, so what is the connection of Fermat's last theorem and Serre's conjecture? Okay, so so suppose you start with a counterexample to Fermat's last theorem. So suppose you have a to the p plus b to the plus c to the p equal to 0 for p a prime bigger than, let's say, 7. Then what Frey looked at the elliptic curve. Okay, I didn't write down the elliptic. You look at the elliptic curve y squared equal to x to the x minus a to the p into x plus b to the p. Right, anyway, you write down some elliptic curve coming from this triple of solutions, and you observe that the mod p representation arising from this elliptic curve has some exceptional properties. Right, he showed, for example, or rather Serre. Okay, so he thought that this representation should be should not exist. Right, but so Serre made precise the reason why it should not exist. So Serre showed, for example, he kind of looked at this as Frey's thing and looked at the mod p representation and did a ramification analysis of this mod p representation and showed that the invariants associated with this mod p representation were 2, right? K rho is equal to 2, the weight is 2, and the level is 2. Right? So the Serre's conjecture would predict that rho arises from S2 gamma 0 2, right? Which is some of the space of holomorphic differentials on some P1, which is 0, and therefore that's a contradiction. Right, so somehow that was how Serre formalized Frey's intuition that somehow the Frey elliptic curve, which is an elliptic curve I should have written. Okay, I could write it, but should not exist. The non-existence was related to, maybe I should write it. Yeah, maybe the non-existence was related to the elliptic curve could well exist, but the mod p representation somehow had too small ramification. Right, so some of this was the curve. If you normalize these numbers correctly. Okay, so this elliptic curve certainly exists if ABC exists, but then the mod p representation has the ramification properties which are contradictory to Serre's conjecture. Okay, so somehow this is part of this kind of Minkowski philosophy that objects with limited ramification kind of struggle to exist. Yeah. So. Okay, so on the other hand, so Serre's conjecture was some sort of vast kind of conjecture, but Ribbit had proved enough of Serre's conjectures, or he had shown that this consequence to a Fermat's last theorem following would follow just from but from the modularity of elliptic curves over Q, right? And then this was proved by Wiles, of course, famously in 1994, and hence you got a proof of Fermat's last theorem. Okay. So in fact, so just to kind of give you some context of how our work kind of one of the strategies of one of the steps of our proof of Serre's conjecture was that so somehow we can give a rearranged proof of Serre's conjecture of Fermat's last theorem using our methods. So our proof was the following: you so look at this mod P representation which Frey constructs, right, which comes from this elliptical I wrote down there. And on the other hand, it has very limited ramification, right? So you start with a elliptical which has a large conductor, it will be the radical of ABC. On the other hand, mod P, the mod P representation, the conductor is degenerated, right? From AB's from whatever, some very large thing to 2. On the other hand, so one would then one could try and say that somehow though this mod P representation should arise from a geometric object like an abelian variety, which reflects the ramification behavior of this mod P representation, right? So one would try to show that this one could try to show that this mod P representation coming from the Frey elliptical in fact comes from maybe another abelian variety, maybe of higher dimension, but that has good reduction outside 2 and semi-stable reduction at 2. Right? So somehow you try to make the representation, the mod P representation come from a geometric object which has the same ramification properties as the residual representation. Right? So somehow our proof of Serre's conjecture, one of the key steps is to prove such statements. And on the other hand, people had shown, Fontaine had shown that such an abelian variety did not exist. Right? So somehow this was a different way of proving, of presenting the proof of Fermat's last theorem. Of course, it looks different and it doesn't directly use modular forms, but the entire proof really depends upon Wiles's breakthrough work on modularity ellipticals. But yeah, it's a rearranged proof, and somehow this was a key step in our proof of Serre's conjecture, this kind of lifting statement. Okay, and in fact, when we first proved Serre's conjecture, we somehow showed some initial cases, and in those initial cases, for example, for primes equal to 2, 3, 5, 7 in level 1, which is to say representations unramified outside L, outside these primes, the representation is not supposed to exist. But the first time such a representation exists, conjecturally, was for the prime L equal to 11, and because the delta function somehow gives rise to a mod 11 representation, which actually is irreducible and satisfies all these properties. And again, our proof used a striking result, which is a generalization of Fontaine-Abrushkin, that or a development of that all abelian varieties over Q with good reduction outside 11 and semi-stable reduction at 11 are isogenous to products of X0 11. So there are two elliptic curves of conductor 11 over Q up to isomorphism. One is X0 11 and one is X1 11, right? But anyway, up to isogeny, there's one. And yeah. All right, so in some sense, okay, so now let me come to the last, how much time do I have? Okay, in the last 6 minutes, let me come to this thing of this book of Bas Edixhoven. Okay, so in this book of Edixhoven, which is called Computational Aspects of Modular Forms and Galois Representations, but they set themselves the task of computing tau p, right? Coming with an algorithm to compute tau p in polynomial time in log p. So some of their task was to come up with a at least theoretically efficient algorithm to compute tau p. Okay, so the main result of this book is for a prime p, the Ramanujan's function tau p can be computed in time polynomial in log p. Right, so somehow this is the basic method of this book is based on Scope's algorithm. Scope, I think in the 1980s, I don't know exactly. He had given an algorithm to compute. So suppose you have an elliptic curve of over a finite field P of Fp. Right, so suppose you look at an elliptic curve E over Fp elliptic curve. Right, you want to count. Suppose you want to count, and this is for various practical reasons. Apparently, it's important to find efficient algorithms to count the number of points of this elliptical. Right, you want to count the cardinality of E of Fp. Right, so suppose you have some curve like y squared equal to x cubed plus ax plus b or something. You want to find, right? There's a point at infinity, but then you want to find the solutions of this equation with x and y in fp. So of course, one naive thing would be to plug in various values of x, right, and then find whether there exists a square root or not. But that will obviously take at least time, which is linear in p and therefore not polynomial in log p, right? So the naive method certainly doesn't give you a efficient algorithm, but Scope remarkably found that you can kind of use the action of Frobenius of P and the Étale cohomology model of this elliptic curve, and that is a better way of computing these points, right? So somehow there was a procedure there was an algorithm to compute points of elliptic curves of elliptic curves using the theory of Galois representation, right? So no, number of points. So the idea, Scope's idea was to do it this mod L for several primes L. Use the fact that and there's p plus 1 minus ap. So you just need to know a and ap is less than or equal to 2 root p. So you just need to do it for sufficiently many primes L. And for prime ap mod L, you can compute using the Frobenius acting on L torsion. Right? But anyway, it seems fantastic that this very elaborate procedure kind of produces you a workable algorithm. But anyway, so but the point was that this was some kind of elliptic curve kind of thing. He was Bass and his co-authors wanted to generalize this to motives of kind of higher dimension, or varieties like the things coming from delta function, right? So so on the other hand, so if you just try to, for example, if you just try to use the definition of tau, and that if you just multiply out this q expansion or q product expansion, somehow you won't get a good algorithm, right? Because then to compute tau n, you need to compute all the tau m's for m less than n, right? And so somehow it won't be polynomial in log of p order, right? So in general, the philosophy of this book was that we hope that, for example, okay, here's this quote. We hope that non-solvable global extension whose existence and local properties are implied by the Langlands program can be made accessible to computation and so become even more useful members of the society of mathematical objects. Explicit description of these fields in the sense those arising from the delta function, for example, make the study of global properties such as class groups and groups of units possible. Certainly, if we only knew the maximal abelian extension of Q as described by general class field theory, then roots of unity would be very much welcome. Right? So in the sense that you can have some abstract theorem which tells you some parameterization of abelian extension of a number field, but over Q, for example, you have a much more explicit statement that all of them come from cyclotomic fields. Right? So somehow one wants to do the same for GL2 type extensions of Q. Okay. So in some sense, Serre's conjecture gives you an answer for explicit class of some sort of explicit class field theory or explicit generation of GL2 finite field valued extensions of Q, which are odd. Okay. Okay, so in the last 2 minutes, let me tell you. So one of the tasks in this book is to compute this K delta L, right? The splitting field of these delta function, the Galois representation coming from delta mod L. Right? So this is done in chapter 7 of the book, and so for this kind of, so in the next, okay, let me write down this table. Okay, it's not very visible, but in that book they write down these polynomials pkl. So for example, we have for the delta function, you have to look at the first 3 cases. So the weight k is 12. I don't know whether this is visible. Okay, the weight is 12, and the primes are, it could have been 11, but okay, the primes are 13, 17, and 19. Right. So, for example, in each case, the value of the degree of the polynomial is L plus 1. So 14, 18, and 20. And the coefficients are fairly large, right? And so somehow they write down these polynomials and they make the assertion that the splitting field of these polynomials exactly give you K delta L, or maybe the projectivized version of the K delta L fixed by the center. Okay. So for this, somehow, I mean, so they wrote down this polynomial, right? To write down this polynomial, there was a lot of work. They used a lot of mathematics, hierarchical theory, this, that. And they also use the fact that delta model actually is congruent to a weight 2 form, right? So somehow then you have the crutch of abelian varieties available. And they do a lot of work to write down these polynomials, right? But on the other hand, these polynomials are written down by using some sort of approximation cutoff arguments. And one is not sure in the end that they do actually what they're supposed to do. Right, so they write down candidate polynomials which should work, and what they can prove about these polynomials is that the splitting field of these extensions of these polynomials is the Galois group is PGL2 of FL. That the extension you're getting, right, which is the splitting field of this polynomial, is unramified outside L and is not totally real. And so and the last thing they get is that they get some estimate on the discriminant of this extension. They can show you that they can tell you that the exponent at L of the discriminant is L plus 10. Right, so somehow they can only study local properties of this Galois representations besides the first global property, which is the Galois group being large. On the other hand, then one wants to tie this to the delta function, right? Because theoretically one wants, though they're pretty sure at this point that this should be k delta L or that k delta L fixed by the center, they're not sure, they can't be absolutely theoretically sure of it, though practically it's pretty, right? But for that they use Serre's conjecture, in fact. So they prove this for this lemma or corollary, it's corollary 3 in that book, in that chapter. So suppose you have a projective representation, right? And suppose and then you look at the corresponding splitting field of this Galois representation and look at the fixed field, look at the field fixed by the Borel subgroup, right? So you'll get typically some extension of degree L plus 1. Now, if the valuation of the discriminant of this extension has this property, then the Serre weight, right, turns out to be k. So in this case, it's supposed to come from a weight k modular form. So if the discriminant has the form L, where L is the residue prime, plus k minus 2, then we suspect, or then they prove that the weight is, then the expected weight of the modular form is k. Okay, so now one applies this to this these polynomials they construct. They can prove that the discriminant is L plus 10. In this case, 10 is 12 minus k is 12 because it's k minus 2 is 10. Okay, so now using this, so essentially, but the problem at this point is that they can only verify ramification properties of the splitting field of their polynomials, but they cannot directly tie it to the delta function. But on the other hand, they check these local properties. And then now if you know Serre's conjecture, then Serre's conjecture will tell you that such an extension does come from delta, right? Because there's a unique Cuspa form of weight 12, which is the delta function. And the corollary is telling you that the thing comes from something. Corollary plus Serre's conjecture tells you it comes from the space of modular forms of weight 12. And there's only one, which is the delta function. Right? So this is a curious application of Serre's conjecture. Serre's conjecture is about going backwards from Galois representations of modular forms. Here you're starting with the modular form. But to actually prove that the algorithm which is written down in the book actually does what it says it does, you really need to use Serre's conjecture. At least it seemed to be at that time. Okay. All right. Maybe I'll stop here. I had yeah. Thank you.
That was a lovely talk. Are there any questions? So you said there's a new proof of Deline's work in this 10-author paper, which is independent.
Yeah, I think it follows Langlands' original kind of strategy of trying to prove properties of symmetric powers and get better and better powers. Once you know automorphy of more and more symmetric powers, you can somehow squeeze the size of the eigenvalues of Frobenius more and more. Yeah, some proof in that style.
So it's a genuinely new proof.
Yeah, because in that case, I think you're in a situation where with a modular form which has no direct connection to geometry. So there is no étale cohomology to rely upon, I think. And yeah, so you're forced to, you don't have this crutch. And yeah. So for example, if you look at a Bianchi form, so a modular form over GL2 of an imaginary quadratic field.
Yes.
The corresponding geometric object is a hyperbolic, is a threefold, so no, can't be algebraic variety.
Yes.
So there is no étale cohomology.
Right.
But this there is more automorphic proof.
I see.
Yeah.
Any other questions?
Knew the delta function before.
There's some question on YouTube. Can you speak a little louder, please?
If Ramanujan knew the delta function before, study of delta function which existed before in geometric way.
Did Ramanujan name the delta function?
Knew the delta function. Study of
who named the delta function?
The delta function as it existed before Ramanujan, but I think he made a deep study of it. I mean, these functions now. Sorry. That I don't know. I mean, Ramanujan doesn't. I mean, he does talk about these functions Q and R, and I think he calls them elliptic functions. I mean, they are sort of functions on space of elliptic curves, but yeah, I mean, he doesn't really. I mean, the proof is the paper is not written in the form of lemma, proof, proposition, proof. There's a stream of calculations, and there are various functions P and Q and R introduced. In fact, I want to go back to the paper because in some sense this convolved sum is equal to sigma R plus S plus 1 and there's sigma R plus S minus 1. Right? So somehow there's and there's also, I think it's related to his there's a famous operator called the Ramanujan theta operator called QD by DQ, and somehow the fact that there are two terms here is related to the fact that you're applying the theta operator to some Eisenstein. Yeah, so there are some various so in fact, I was Serre. I mean, the question is whether Ramanujan thought in terms of modular forms, right? So Serre kind of said that it didn't matter, right? Because to Ramanujan it was not important whether he new modular forms or not. He knew enough for what he wanted to do. And somehow the fact that the delta function has this Euler product expansion, which somehow seems to be of degree 2, Serre suggested that means somehow he was aware of the connection with GL2 and modular forms. But yeah, I have not, first of all, I have not made a deep study of this paper, but I've looked at it a few times. But yeah, he may have, I don't know what his pre-knowledge was before this paper.
Any further thoughts or questions? Yes.
I'm going to probably visit this when you spoke about it. So you had mentioned about this Langlands conjecture, the tau n is
Not equal to.
not for density. So what is the notion of density there? Is it the display density or the density in the sample?
I think you can use the weakest notion you want, but still it would be. But no, the lemma conjecture is tau n is not equal to 0 for all n. The lemma conjecture is known for density 1, I think. Tau p is not equal to 0 for a density 1 set of primes is known. Yeah. I don't know, but I think you can probably take any notion of density you want. For example, Dirichlet density, yeah. But I think the more subtle, the harder the question of whether tau p is not congruent to 0 mod p, that's kind of totally unknown. I think. The tau p not equal to 0 is supposed to happen for all primes p, tau p is supposed to be not 0, right, by lemma. And that is known up to density, up to error term of density 0. Whatever notion of density I think you want, yeah. But the subtler question of whether tau p is congruent to 0 mod p or not, or the question that tau p is not congruent to 0 mod p for infinitely for density 1 perhaps primes p, that is totally unknown. It's not even known as for whether this should whether this happens for infinitely many primes p. Though as you see, it's exceedingly rare. Up to 10 billion, there are only 5 or 6 values for which it is. Yeah. I think I looked up the Wikipedia entry once about how people found this prime 7 billion.
Right.
Yeah, but I've forgotten what the story was. Do you know
I was going to ask.
Yeah. I don't know how people find such frighteningly large primes.
Any further thoughts? If not, let's thank Shekhar for the lovely talk.
Thank you.